So we get to pressure and depth, which is about fluid dynamics. And this is a lot easier because we use calculus um, for the logic here. Or we don't use calculus for the logic here. And before we used calculus um, with a lot of things and with a lot of proofs, which is why some proofs couldn't be proven. Like, for example, our book tells us nothing about rotational energy. Um, and how it's added to the rotational system, which is something with, I guess, the binomial expansion theorem, and it has doesn't talk about how the fourth kinematic equation is a dot product and how that ties in with the scalar component. In fact, it even uses the fourth derivative, or not the fourth derivative, it's the fourth kinematic equation, which is a dot product. So that means it would essentially have nothing. It's a scalar, and they use the scalar component and identity to solve the work energy theorem because they use the fourth equation again, but the fourth equation relies on calculus. So everything is the foundation of calculus. Now, in the same way, you can probably apply a little bit of calculus in this sense, but instead, I'm going to take the algebra route. And the thing about algebra routes is that they can sometimes be a little bit not misleading, but they can be a little bit off with precision. And the thing about math is that I like everything to work out perfectly. But in this case, it would work out just very, very precise. So maybe you can do like an epsilon delta proof, as mentioned. So, anyways, imagine a vertical column of water. So, I mean, I'm just going to conceptualize it using basic logic. If you put your hand in a pool, it won't hurt, but if you put your hand at the bottom of the ocean, the water pressure will just hurt you a lot because water pressure increases with depth, and that is the logic there, and that's the entire chapter essentially um, in 1 second. But now we have to do the proofs. So yeah, so imagine a column of water, and notice that we're dealing with static fluids here, nothing with dynamic fluids. In fact, if you look into fluid mechanics, they're doing some pretty interesting stuff with the Navier-Stokes equation. In fact, they've been working on it for a long time now. It's one of the 7 Millennium Prize problems. So maybe you can solve that in the future. I think only one has been solved, and that's by Gregory Perelman. So take a container of water, and inside, let's just say that we have a rectangle, or I guess yeah, a rectangle, rectangular prism. So we know that, and again, these proofs are kind of faulty because we don't go to calculus, and in calculus, I'm sure they'll prove it using um, some form of geometric, um, I guess, geometry, algebra, calculus intersection. Here we just use the intersection between geometry and algebra. So it would work in this case, but again, the proof given here works for all cases as well. So somehow the proof we managed to derive is working anyways. Working regardless of whether we solved it in a very, very precise manner. It's kind of like the same way, like think of like filling up a balloon and filling up a tire. Those are two completely different actions, or not actions, those are two completely different items, but filling up a balloon will give you the same exact um, solution as filling up a tire. You just pump air into it, and that's kind of the logic here. We're going to figure out how to derive this proof using a rectangle, and somehow it manages to work for everything. So first, let's take the objects. Well, we have to use Newton's second law. So as we know, we're dealing with static fluids, meaning the fluid is not moving. So that means F bottom must equal F top. I guess equals Ft, B and C. I think for logical sakes, we'll use 2 and 1, 2 being the bottom. Now, since it's a rectangle, we can assume that the bottom pressure is going to be P times A. And we can assume that there is no gravity acting up on it because gravity doesn't act upwards. So it'll be P to A. And since we know that rectangles have the same area on the top and the bottom, we can rewrite force 1 as P1A plus gravity, which is just going to be mg, which is just going to be the weight of the water. So here's what we can do. Well, we know that density is equal to mass times volume. So that means we know mass is equal to density over volume times, density over volume. Density over volume. Oh, sorry. I was like, okay, yeah, that makes sense. Oh, I wrote the equation wrong. It's D equals m over v. I was looking at it and I said that's not correct. Well, mass is equal to the product of density and volume because density is just mass over volume, and then times volume just gives you the mass. So we can plug that here. But we know that, oh, sorry, I put the D term again. So we can rewrite this as P1A plus dVg. But we know that volume is just equal to area times height. So it's going to be P1A plus the area of the top times height times g, and is equal to P2A. So we'll divide A on both sides, so we have to remove A from every term, giving us that the pressure at the top is equal to the pressure at the bottom, or the pressure at the bottom is equal to the pressure at the top, plus density times volume times gravity. And they use rho here, which kind of looks a little bit like a P. So I'm not going to use it because we're using pressure here. So the logic is going to be equals P0 plus dVg. And that is probably the equation you'll have to memorize. I prefer personally dVg over d uh, over rho gh or oh wait, dhg. Oh, sorry, this is a h because we divided volume. Oh, yeah, because we took out area. So it's going to be equal to dhg. And this is way, way more preferred. So this essentially calculates the pressure at the bottom or at any point of the fluid. And this pressure will be the pressure on top of the surface. And then this would be depending on how deep you are at the water. So that is the logic there. So we'll move on here. Formula in English, the P bottom equals the P top plus density times gravity times height. Pretty logical. This is another proof I was doing, but I never got around to it. This means pressure depends only on vertical depth. It does not depend on container shape, horizontal width, or total volume of water, which makes sense because gravity is only a downwards acting force, while with the force on top, while with the force to the side if it matters, especially if it's a static fluid, which means that there is no pressure on the left or the right. Um, there's no, there's no pressure acting from gravity on the left and the right. Um, so yeah, that's the logic there. So that is pretty simple. And why does horizontal distance not matter? Again, gravity only acts vertically, only vertical weight of the fluid matters. Um, so going over the equation again, PO is the pressure at the surface of the fluid, which can be any medium. If it's an air medium, then PO equals pressure atmospheric. And DHG is just the pressure acting from that vertical column of water. So if this is a case of water, then that would be the case. So that's all fluid dynamics for 11.3 at least. So that's logical. So yeah.